For decades, we've been told a story about our universe, that it's not just expanding, but it's actually speeding up, pushed along by some mysterious force called dark energy. But what if that whole story is wrong? What if the acceleration is just an illusion? Today, we're diving into a really radical idea that says the answer isn't a new force, but a totally new way of thinking about time itself. Are we on the brink of a cosmic revelation? Let's get into it. So this is the big question, right? This is the mystery that's had cosmologists scratching their heads since the late 90s. They were looking at these distant supernovae, these massive stellar explosions, and they realized they were dimmer than they should be. And that could only mean one thing. They were farther away than our models predicted. It was like the universe hit the gas pedal, and suddenly, nobody knew who was driving. And this really leaves us at a fork in the road with two very different ideas. On one hand, you have the standard explanation. There's this invisible, mysterious force, dark energy, acting like a cosmic anti-gravity pushing everything apart. But on the other hand, a wilder theory suggests there's no new force at all. Nope. It says what we're seeing is just an illusion, created because we happen to live in a gravitational slow lane, where our clocks just tick differently than the rest of the cosmos. Okay, so let's quickly touch on the mainstream view. Dark energy, well, it's basically a placeholder. It's a fudge factor in our equations that makes everything work. We think it makes up almost 70% of everything in the universe, but we have absolutely no clue what it is. I mean, it is literally the single biggest puzzle in all of modern physics. All right, but now for the challenger. Instead of just inventing some new, mysterious energy to solve the problem, Timescape Cosmology comes at it from a completely different angle. It suggests a solution that's rooted in physics we already know and trust, Einstein's general relativity. Let's see how this thing actually works. So here's the absolute core of it. This theory, from physicist David Wiltshire, says that the acceleration we think we see isn't real. It's just an observational effect. Think about it. We live inside a galaxy, right? That's a spot with a lot of gravity. And what did Einstein teach us? Strong gravity literally slows down time. So if our clock is running slow, when we look out at the rest of the universe, it's going to look like everything else is speeding up. Now, this whole idea hinges on one simple fact. Our universe is, well, lumpy. It's not smooth. It's made of these mind-bogglingly huge empty areas called voids. That's about 70% of it. And then these dense, web-like filaments of galaxies, which make up the other 30%. And us, we live right in the middle of one of those dense, lumpy bits. Here's a great way to picture it. The dense galactic filaments are like deep gravitational valleys. Down in these valleys, clocks tick a little more slowly. But the vast, empty voids, they're like cosmic mountains with much weaker gravity, where clocks tick faster. We're stuck down in a valley, looking up and out at the mountains, and that difference in the flow of time creates the illusion of acceleration. And get this, the difference we're talking about here isn't tiny. It is absolutely staggering. The theory calculates that a clock right here in our Milky Way could be running up to 35% slower than a clock just floating out in the middle of one of those giant cosmic voids. That is a massive difference, and it might just be enough to explain everything we see without needing any dark energy at all. Now look, this is a pretty radical idea, and it's definitely not without its critics. On the plus side, it actually seems to fit some of the newest supernova data better than the standard model. It could even solve another huge headache in cosmology called the Hubble constant tension. That's a big disagreement on how fast the universe is expanding. But on the other hand, it has a tough time explaining data from the really early universe, and it is for sure still a minority view. So how on earth could we ever settle this debate? Well, the answer is just as bold and ambitious as the theory itself. To figure this out, we need to get out of our gravitational valley. We have to go out there and directly measure the flow of time in deep space. And believe it or not, scientists actually have a plan for how to do it. The proposal is, honestly, it's straight out of a sci-fi novel. We're talking about sending a whole swarm of tiny, gram-scale probes on an interstellar journey to Proxima Centauri. We'd blast them with powerful lasers, getting them up to a fraction of the speed of light so they can travel from our sun's gravity well across the flat plains of interstellar space and into the gravity well of another star. And just to be clear, this is not a weekend trip. This is a journey that will likely outlast many of us. We're talking about a multi-decade mission. These probes would launch, accelerate, and then just cruise for over 20 years before they even get close to their target. It's a truly monumental undertaking for a truly fundamental question. And while they're on this epic journey, these little probes will be running 3 incredibly clever experiments designed to measure the actual fabric of space-time itself. All right, so let's pop the hood and see what kind of futuristic tech we'd need for a mission like this. What's in the toolkit for this interstellar quest? First up, and this is so cool, the fleet is basically going to turn our own sun into a giant natural telescope. By flying way, way out there, they can use the sun's gravity to bend and magnify light from those distant supernovae with insane precision. Then, after a 20-year trip, they'll do the exact same thing using Proxima Centauri's gravity as a lens. And the amplification you get from this technique? It's nuts! We are talking about making something look up to 100 billion times brighter. That's a level of power way beyond any telescope we could ever hope to build, and it's powerful enough to spot the tiny, subtle differences predicted by the Timescape model. Okay, method 2 sounds like it was ripped from the pages of a sci-fi script. The probes would have these tiny quantum computers. As they fly through different parts of space, they'll measure how the local lumpiness of space-time affects delicate quantum states like the entanglement between different probes. It's basically using the weirdness of quantum mechanics to map out the geometry of the universe. And finally, the third method is the most direct test of all. Just stick some super accurate atomic clocks on board and see what they say. But, and this is a huge but, there's a major challenge. The probe's incredible speed makes its own clock slow down by about 2%. The actual gravitational signal they're hunting for, the thing that could prove the timescape theory, is less than 0.1%. So the whole game is figuring out how to perfectly subtract that massive speed effect to find the tiny, tiny signal hidden underneath. But if, and it's a big if they can nail that calculation, this network of clocks becomes the ultimate truth teller. It will give us a direct measurement. Does time really flow faster once you leave our sun's gravity and get out into deep space? This would be the definitive test of the timescape. So you might be thinking, wow, that is an incredibly complicated, decades-long mission. And you'd be right. So why bother? Why go through all this trouble? Well, because the answer this mission could find might just reshape our entire understanding of the cosmos. Because what we stand to gain here is, well, it's almost everything. This is about more than just dark energy. It's a brand new way to test Einstein's greatest theory on scales we've never reached before. It could spark a revolution in how we even think about time. And just imagine the leap forward in interstellar technology we'd make. Honestly, whether Timescape is proven right or wrong, the results would be world-changing. And that leaves us with this one final, mind-bending question. Is it possible that we've been missing a fundamental truth about the universe just because of where we happen to live and how our clocks happen to tick? The answer, it seems, is waiting for us out there among the stars.